Systems are designed to grow. We add resources, we upgrade parts, and we expect more output. But often, the result feels like the opposite. The system gets slower, less efficient. So why does this happen? In this explainer, we're going to break down the structural reasons for this common paradox.
At its core, the issue is a conflict between our expectations and the reality of how complex systems actually behave. Our intuition tells us that if we improve a part, the whole system should get better. It just seems logical. We expect faster output, but instead we experience more delays. We invest in efficiency only to find ourselves facing growing gridlock. This isn't just a coincidence. It's an entirely predictable outcome that's baked into the very structure of the system.
The source of this slowdown is rarely a single broken part or a poorly performing team. Instead, the bottleneck is what's called an emergent property, an outcome that doesn't come from any single piece but arises from the interactions between all the components of this system itself. To understand this, we can model any system as a simple chain of interconnected processes. Think of it like an assembly line. Each process in the chain takes an input from the step before it, performs some work, and then produces an output for the next step.
The key measure of success for this entire chain is its throughput. Throughput is just the total amount of work the entire system completes in a given period of time, let's say units per hour.
Now, each individual process within that chain has its own performance limit. We call this its capacity. This is simply the maximum rate at which that one single step can process inputs and create outputs.
So what happens when inputs arrive at a process faster than its capacity to handle them? Well, a waiting line forms. This accumulation of work in progress, this backlog, is called a queue.
And here is the fundamental reason bottlenecks form. In any real-world system, the capacities of each process are never perfectly balanced. It's just not possible. There is always going to be some variation.
Let's visualize this with a simple three-step system. First, we have process A, which has a capacity of 10 units per hour.
From there, the work flows to process B, but process B is slower. Its maximum capacity is only 7 units per hour.
And finally, we have process C, which is actually the fastest of the three, with a capacity of 12 units per hour. In this chain, process B is clearly the slowest step. This makes it the system's constraint, or what we more commonly call the bottleneck.
And here's where the problem starts. Process A is feeding units to process B at a rate of 10 per hour. But process B can only get through 7 units per hour. This mismatch means work starts to accumulate right in front of process B.
So, after just 1 hour of operation, process A has sent over 10 units, but process B has only managed to complete 7 of them. A queue of 3 unprocessed units is already formed. After 2 hours, that pattern just continues. The queue now doubles to 6 units, and this accumulation won't stop as long as the system is running, creating bigger and bigger delays.
This one single local constraint creates massive system-wide consequences. Downstream, process C is basically starved for input. It's only getting work at the slow pace of the bottleneck. And upstream, process A will eventually be forced to stall because the queue in front of B will just get too big.
And this is the crucial principle. The throughput of the entire system is capped by the capacity of its bottleneck. The chain is only as strong as its weakest link. So even though process C can handle 12 units an hour, the system as a whole can only produce 7.
Okay, so in our initial state, process B is the constraint, and our total system throughput is stuck at its capacity of 7 units per hour.
A pretty common response to this is what's called a local optimization. We focus on fixing the bottleneck. Let's say we invest in improving process B, and we increase its capacity to 11 units per hour, which now makes it faster than process A.
Problem solved, right? Well, with process B now running faster, the constraint hasn't been eliminated, it's simply shifted. Now, process A, at 10 units per hour, is the slowest step in the system. It becomes the new bottleneck, capping the entire system's throughput at 10.
This really reveals the true nature of a bottleneck. It's not a flaw in a component that you can fix once and for all. It is an inevitable property that emerges from the simple fact that you have different capacities across the entire system.
And what that means is that efforts to grow a system or optimize its performance don't actually get rid of constraints. They just cause the constraint to shift from one part of the system to another. There is always a bottleneck.
This leads us to a final, structural question.
If every system is guaranteed to have a constraint, and improving one part only reveals a new constraint somewhere else, what does it truly mean to improve the performance of a system as a whole?